Hey everybody, I'm Eric Ronald, Principal Consultant with SRK Consulting. I wanted to share this video today. It's of my recent presentation that I gave at the SME Annual Conference on the 26th of February, 2025. The aim of this talk is to provide a general overview of geologic characterization for lithium pegmatites. I'm going to provide a brief summary of some of the commonly observed issues that we come across from work, whether it's due diligence or project work, exploration work, some of the challenges that we see, along with some of the good practices that are out there on really to assess the mineral resource risk associated with lithium pegmatites. All right, so a lot of people ask, is there even a market for lithium, right? Lithium really peaked back in 2022, 23. We can see the highs of the curve here on the screen. Everything was going gangbusters. We had a lot of different types of projects that were being assessed from top world-class, top-tier projects all the way to marginal lower tier projects. Obviously, when economics and market frenzy drive it, we see anything and everything that is being assessed and kicked around. Well, over the last about 6 to 12 months, we've seen more of a stabilization, significantly a drop, and also a stabilization of prices with lithium. And due to that, with that stabilization, we're starting to see a recent pickup in mergers and acquisition, and certainly a lot more due diligence, looking at these top tier assets. But there are still a lot of these marginal sort of mid-tier projects that are out there that are still being kicked around due to those high pricing from just a few years ago. Now, when we look at the past, we look at market projections going forward. The consensus among analysts and among the market in general is that we'll see a supply deficit starting in about 5 years from now, around 2030. With that, we expect there to be continuing demand. Certainly, we feel that there is a market for lithium, and right now may be a fantastic time to start looking at some of the mergers, acquisitions for some of these higher quality assets. Of course, that relies on the technical work that has been done, the ability to assess risk, and the ability to actually mine and recover lithium from a lot of these projects. All right, so a very, very high level, quick brief on different deposit styles for lithium. The main ones that we see out there that are potentially economic. The first being lithium brines. These akin to salar deposits. We see them in Clayton Valley, Nevada, Atacama Desert of Chile, and more focused within South America in general. Now, these brines require significant detailed hydrogeologic characterization and are a bit of a different animal from the traditional hard rock mining. What I'm going to be focusing on here in this video is really those hard rock deposits or the pegmatite-hosted lithium. But there's also some others that have grown in popularity over the last few years. These would be the sedimentary or the clay-hosted deposit. Think of ones specifically in Nevada, where we have Thacker Pass, Rhyolite Ridge. These are a bit more complex, tend to be lower grade, requires a lot of detailed lithochemical and mineralogical work to really understand the recovery and ability to metallurgically assess those. Anyway, let's focus a bit more on those hard rock pegmatite deposits. All right, so we can't talk about pegmatites without talking a bit about chemistry and mineralogy. Now, I don't want to get too much into the weeds on this, but this is absolutely critical. Now, the reason why these are lithium bearing is they're a unique sequence or unique grouping of pegmatites that we call LCT, just short for lithium, cesium, tantalum. So the mineralogy that we often see with these, primarily quartz, case bar, albite, we see muscovite. There tends to be a lot of enrichment in fluxing components. So a lot of hydrous minerals. We see boron, we see phosphorus, and a bit of fluorine is quite common. So the minerals that we care about, the minerals that are potentially economic and lithium bearing, these would be the spodumene, lepidolite, pentolite. But we also tend to see a lot of tantalite. There's some considerite, apatite, beryl, and the list is on the screen here. Now, one of the tricky things with the mineralogy and the chemistry of these pegmatites is that often, because these are either located in active or historically active hydrothermal systems, often we see clay alteration of the spodumene lepidolite, which can be very destructive to those minerals and thus have massive impacts on the ability to recover lithium from the processing. Now, things like grain size and texture can be very, very important based on the processing. So these are things that absolutely have to be assessed when looking at these types of deposits. Just like the good stuff that's in there with the spodumene, lepidolite, we have to assess those deleterious chemistries and mineralogy. These can cause absolute headaches, increased cost of processing, beneficiation. The main baddies that we seem to come across with these, iron is by far the biggest one, but fluorine, sulfur, and potassium also have additional challenges, often can be removed from the system, but just result in increased pricing. All right, so the emplacement of these things. These are absolutely fascinating geologically and can be rather complex. So what we see from a general emplacement and a genesis of the deposit is we have that parental granite, fractionization within that, and a volatile enrichment and zonation. You see my cursor on here. We often see these pegmatites forming off of portions of the intrusive in a highly fractured environment that basically push out from that main intrusive. So as the temperature drops, as you move away from that intrusive, we tend to see an increase in albanization, basically a replacement of those calcium feldspars, plagioclases, micas with sodium, sodium-rich minerals as a metasomatic replacement. As this sort of simplified graphic shows, is that they are fantastically zoned mineralogically and chemically. Now, they don't always, this is very academic here, of course, but as you go out, we see more of a barren zone at the middle, beryllium-rich zone, and then followed by the chemistries as we sort of move away. These are fantastic to use as a general model for exploration in these areas, but we all sort of know that, that life tends to be more complex. And if there are multiple impulses of the parental granite, of intrusives, the complexity of not only the host rock chemistry, of the structure, of that pressure temperature environment as it moves away from the intrusive, things can move around and change a fair bit, that's for sure. So here's a kind of a real world, just quick example of how we see this zonation. Just taking a look at a little piece of the planet over here where we have an operating lithium pegmatite operation. So if I throw a bit of geology on here, there's a lot of Cenozoic and tertiary cover in here, but we know that we've got metavolcanics, metasedimentary, and some banded iron formation within this general trending syn form. Off to the southeast there, we have that parental host granite, which is the source of the LCT pegmatites. As these pegmatites come into the system, flow along the major structures, we start to see the emplacement and the deposition of the various mineralogies and the chemistries. And so in this case, we know within the banded iron formation, you see some pits there on the screen. Those are some iron ore pits. But where the pegmatites are, we do see that zonation, historically mined tin, currently mined lithium and tantalum. And then we have a beryl-bearing pegmatite further to the south. So it's not just pure theory. We see this in practice in the field, which is a really cool thing. But it does it is a very complex system, complex from a chemical and certainly from a structural. So that distance, the age, and the timing, and the chemistry throughout this whole system and this property or this district scale is absolutely critical to understanding the potential for lithium, the emplacement of lithium, where it is. You need to ensure that there's some sort of receptive host rock, that the chemistry, the geometry of it, and that fertility of the host rock allows for mineable volumes and emplacement of the pegmatites. We obviously need plumbing, right? Any sort of hydrothermal system, those structural conduits, the complexity of the structure is absolutely key into where these are, as well as prediction and emplacement of the pegmatites. In a case that we're looking at right here, we've got multiple deformation events, and it is very, very complex. And so pegmatites tend to be very challenging on trying to predict where their emplacement are and consistency of, say, thickness in mineralogy. So on that, we take a look at kind of the geology map of the mapped geology of this particular area. You get an appreciation for the complexity here. It is placed within a regional plunging sinfold. There's multiple deformation events, and those deformations the pegmatite emplacement is in deformation, adding to the complexity. We also see drag folds in here, and basically the sum of this is that these are simple from a conceptual deposit model, as most things are, but the reality tends to be very much more complex. So assessing the structural geology, 100% critical into understanding both the emplacement, the continuity, the thickness, the mineralogy, and so forth of these lithium pegmatites. They're primarily controlled by the structure, right? These are the plumbing of the system that allows the emplacement of the dikes. So the folding, the faulting, but also details of foliation, jointing, and other discontinuities play an important role in the emplacement of these. They are rarely linear. There are a few places around the world where we are fortunate enough to see large linear emplacement, but often it is very complex. So really understanding the timing of what is post-syn and pre-mineral emplacement of these pegmatites is absolutely critical. At the end of the day, they are dike swarms, right? They do not like to behave as we hope they do, especially that's conducive for mining, whether it's open pit or underground. They tend to be highly folded, both interior and just at a deposit scale or property scale. They can be very lenticular. They will pinch and swell. They will pinch out, disappear, show up, what seems almost randomly. Obviously, that is controlled by the different deformation events, but trying to work that out can be an absolute challenge. Oftentimes, we do see a bit of alteration within the wall rock, and based on the chemistry of both the host rock and the emplacing pegmatite, we often see ion exchange. And so the chemistries of the pegmatite that is emplaced in different country rock can have a slightly different geochemical characteristics. Now, that may have impacts on recoverability and metallurgy, so they need to be assessed. And because these areas are structurally complex, we know there's a hydrothermal system, the emplacement of these pegmatite dikes. Often it's not just a single intrusive event, but multiple pulses, or potentially later stage cross-cutting features that we often see associated with lithium pegmatite dikes. Those pesky, often skinny mafic dikes or doleritic dikes that we see cross-cutting, but sometimes it's just barren quartz that comes through and cross-cuts. So these are all critical aspects to trying to assess how much material is actually there in the ground and the continuity of these. All right, so if we are fortunate enough to see a significant multi-meter wide pegmatite emplacement, there often is a bit of zonation associated with the pegmatites. Think of these as a vein system. That's pretty common to see both internal dilution of grade, but also the zonation of the pegmatites. Now, each one tends to be a bit unique, simply because those environments of emplacement are rather unique. They don't always have to be zoned. There are plenty around the world that are well mixed and rather homogeneous and consistent, and that's fantastic from an assessment and a mining perspective, but we need to understand that during geological characterization. Also, as these approach the surface, now whether it was in a highly weathering environment that was subject to oxidation or a supergene enrichment near the surface, lithium ions can be quite mobile, and we often see a surface leaching of those. which results in, say, surface trenching, showing lower lithium grades than would be a bit more in situ at depth. So the understanding of that oxidation, both from a surface as well as in association to recent structures that may be flowing or may be containing meteoric water, that would result in some of that oxidation or that enrichment or depletion, is absolutely key. Again, these tend to be placed in rather structurally complex environments, and so understanding the interaction between the structure, any sort of recent fluids, and these pegmatites is very important to understanding tons and grade that's in the ground. When we do see internal dilution, now this could be internal dilution just from barren zones, zonation of the pegmatites, or xenoliths of country rock that have sort of been rafted off and emplaced within there. These often are an absolute challenge to try to assess. They're almost pure nugget in many cases. You hit them, you don't know how big they are, depending on your drill spacing. So understanding an appropriate level of drill spacing from a resource perspective can be key for all of these aspects. All right, so good evaluation of this. Speaking of drilling and sampling, there are a lot of different drilling and sampling methods out there, but really the only one that tends to show the highest confidence is, of course, diamond drilling. Now, during early exploration, it's pretty common. You see surface trenching. Maybe there's some outcrop of pegmatite. The cheap and quick thing to do would be some surface trenching, try to assess thickness, and that's perfectly fine, and that's excellent. That's normal exploration procedures. But to understand the impact of using that data as it relates to mineral resources, it may not be terribly helpful. I mentioned some of the surface oxidation, which may result in a reduction of lithium grades. The thicknesses may not be a true thickness from a trench, right? These things tend to have a lot of different attitude changes, not to mention thickness changes. Now, RC, any good exploration geo worth their weight loves RC. It's cheap. It's a lot faster. You can get a whole lot of powdered samples, as you can see from the image here, where we've got some nice lithium intercept here with some country rock around it. Nice black and gray or black and white rock here. Okay for initial assessment, but caution when the majority of a deposit is assessed by RC chips. All those items that I've just been talking about, how critical the mineralization is, the mineralogy, the petrography, the structure. Well, you're not going to get any of that from RC chips, right? I mean, maybe a little bit of mineralogy, a little bit of alteration or whatnot from the chips, but not confidence in the structure, and that's absolutely key. So when it comes to good assessment and evaluation, diamond drilling is certainly the way to go. Larger diameter core, the better, right? Because items like grain size and variability of mineralogy is key. So looking at HQ and PQ when possible to really get that good confidence in the understanding of structure, context, alteration, mineralogy, so on and so forth. So in order to get those, we need analyses, right? Mineralogy, of course, this is important. If I haven't beaten that horse to death yet, I'll continue to do so. But understanding, okay, you've got lithium in the system from a chemical perspective, but what is it hosted in? Is it hosted in highly altered clay minerals that are not going to be able to be easily or cheaply beneficiated or to have product produced? Or is it in a spodumene or lepidolite, something that can be more easily turned into a product? Understanding the texture and the grain size, that does impact recovery. So on the chemistry as well, understanding the trace chemistry, the impurities, right? So going out and just grabbing lithium grades from everything, well, that's not going to work. That from maybe early days exploration to get an understanding of what's there and what's not, you'll get a free pass on that. But after that, if you have any sort of assessment on resources or reserves, that trace chemistry for the impurities is absolutely key. And I've said before, and I'll say it again, iron is one of the worst baddies. It just results in challenges downstream. Now, those challenges can be accounted for, but it has cost implications for the economics of the project. So assessing the type of iron, The host mineral of the iron, the ability to remove the iron from the system is absolutely key to understanding that. So a combination of chemistry and mineralogy. And a bit of a, maybe not a side, but just as critical with analysis is that with lithium pegmatites is understanding the digestion, working with your lab, working with your geochemist is absolutely key. Minerals like spodumene, cassiterite, and others can be very resistant to digestion. So using a 4-acid digestion is not going to be sufficient enough. And then obviously a lithium boron flux on any ICP doesn't make any sense if you're trying to test for lithium, of course. So working with the chemist and the lab is important so they understand what you're trying to achieve out of this. But it's also important for historical assays that if you come across a property that does have historical information, geochemical work, to understand how was the digestion, what was the method of analyses that were done. Obviously, a peroxide fusion needs to be done. And again, any good geochemist in a good lab will be able to sort that out for you as far as assessment goes. Impurities, just like a lot of other industrial minerals properties, it is just as critical to understand both what we have from an economic point of view, economic mineral point of view, but also the impurities can make or break your deposit on whether this is economic or not. The main bad ones that we see, again, are iron, fluorine, potassium, sulfur. There are some others. Again, it comes down to costs of either mining, processing, or beneficiation to get proper product. So there are several elements that we do see that do track through to the spodumene concentrate for the final product of these. And again, iron tends to be the big bad one. Now, in many cases, the iron is mixed in with the pegmatite, as we see from the core images over here. So it's, like I said, it's not always a easy beneficiation process. And at the end of the day, when we talk about product, the spodumene concentrate is really worth whatever someone's willing to pay for it. So the better the specifications, meaning the lower impurities, the higher the value there is. But that offset with the cost of beneficiation in order to get your deposit from whatever Mother Nature provided to actually into a proper spodumene concentrate may be a very costly and cost prohibitive exercise. All right, through evaluation, obviously, we go through the standard paths of taking all of our drilling information, turning it into nice 3D geologic models, and then turning those into a resource block model. But this can be a big challenge in many cases. Oftentimes, with projects that are lithium pegmatites in large pegmatite swarms, is initial drilling might be a bit wider spacing, might be all at the same angle, maybe just vertical, or all directional drilling from one area, say from the east 45 down toward the west. Now, if we take a look at the pictures here, we kind of get an idea of an old open pit, and we see the pretty common lenticular starting, stopping, variable thickness. It's a dike swarm, right? It does not behave terribly well. We see little pods that kind of come in and go and whatnot. Well, depending on your drill spacing, this can be an absolute challenge to try to represent continuity across drill holes. And you can imagine here, if a drill hole was dropped right in the middle, you probably wouldn't get anything, and then you drop one right over here and it shows nice big thickness. But we follow this vein, this dike up, and it just sort of disappears. Now, how do you translate that into a good 3D geologic model? Well, you do the best you can, right? In this case here, this is just one section where there's just a handful of drill holes on here. Try to best represent that as best you can. Obviously, when you first start, you may not really understand the orientation of all these dikes, so you may end up a case like this one over here, where you're drilling right down the plunge of one of these dikes, which doesn't give you a whole lot of information. But now, the other bit is that when we are going through these, to make sure that geologically, if we do identify barren dikes, late mafic dikes, other major features that do impact, whether that's through dilution, cross-cutting relationships, or whatnot, to the lithium pegmatite dikes, that those are modeled. Small scale can be absolutely challenging, or understanding the orientation of those can be absolutely challenging. The other bit with 3D geologic models is that year to year, as you add more drilling, expect to see potential massive changes in the volumetric representation of your 3D models. So you can imagine here, if you've got this deposit that we're looking at here, and you've got these 4 drill holes, and say that's all there is. Obviously, this site has more. You're going to come up with a pretty simplified interpretation. Next year, you come in and you double those drill holes, right? And you vary those angles, and you start to understand that maybe these two are connected and maybe it doesn't go to surface. Maybe there's something else that's offsetting. And we start to eventually, with enough drilling year on year at various angles and orientations using core, to start to create something that is actually what it looks like once it's been mined out, right? What Mother Nature has provided. That lenticular, that starting, that stopping, that complex structural environment that comes into it. So early days projects, PEAs, sometimes even PFS, you have to understand that things may change with more drilling and as projects are developed. More so than you see in other deposits, I would say. Other common issues that we tend to come across when we look at modeling, oftentimes we see extrapolation of volumes between the real wide space drilling. Everyone wants to connect dots between, 300-400 meter space drilling. Maybe that's the case, maybe it's not. Because of the complexity, whether it's structure or these dikes, it's probably unlikely, but you don't know until you either drill it more or you mine it out, right? Really modeling and understanding this structural complexity can be a challenge, right? And not only from a scale perspective, but also just having enough data. You may be undercover, you may not have any outcrops, you may not have enough drilling to really get an understanding of structural complexity. But oftentimes, one of the key items that we see on successful projects are companies that do focus heavily on doing a good structural model and a good structural assessment of their property. Volumes are terribly difficult to try to model consistently between drill holes because of all the reasons of inconsistency and discontinuous nature of these. That sort of saprolitic leaching zone, that oxidation we see, definitely needs to be accounted for. Sometimes we come across this issue where people are having, modelers have taken the lithium pegmatites all the way to the surface and had the grades just go all the way through. That may or may not be the reality based on the environment. Also, in large dike swarms, often there are multiple pulses of events that come through, and there may be lots of pegmatites that have no lithium-bearing minerals associated with them, like pure quartz or feldspars that come through there, or those pesky mafic dikes that come late. Now, they need to be understood, modeled, and you can't just go on white rock good and other rocks bad. Right? So the detailed work on structure, lithology, geochem, mineralogy, mapping, etc., is absolutely key to try to make these models as good as you possibly can. Early days projects, obviously, it's a bit of a struggle. We see some common oversimplification of models in many cases. That's a bit of a challenge. And then missing those diluting features, right? Whether that's xenoliths, those lake stage dikes, barren dikes, whatever it may be. So all of this information goes into our resource estimation, right? And there can be absolute challenges if we struggle on how we collected that fundamental data, the drilling, the mapping, the structure, all of that's feeding into our resource estimation. As they say, garbage in, garbage out. You can do the best you can with what you got, but realize there may be material changes as these projects develop and have more work done on them. So those estimations of grade, bulk density, mineralogy, and all these other attributes can absolutely be challenging. So it's so critical to focus on those fundamentals of understanding the structure, the genesis, the mineralization, the timing, and so forth of these deposits. That's just lead to better confidence associated with your resource. When we look at some of the items that are a bit more challenging to estimate, that are non-additive numerics, things like grain size or other attributes, oftentimes we can get a bit creative, look at semi-quantitative approaches like relative size bends to just look at relative spatial distribution of, say, grain size within parts of the deposit. And so there are some ways that we can try to better assess this without getting too complicated based on the information we have. And there's certainly some other geometallurgical categories that can benefit from, say, a nonlinear estimation or simulation techniques. Now, this is one of those that we see more challenges when it comes to the fundamental data acquisition. So the application of more advanced resource estimation is often not recommended because we do not have confidence in the underlying data, right? And so there is no amount of, as they say, fancy math that's going to clean up or improve the confidence if there's an underlying misunderstanding of structure, mineralogy, chemistry, and so on and so forth. If the deposit's really well defined, then there can be benefits for using some of these. And ultimately, when we talk about geometallurgy, whether that's dilution, whether that's xenoliths, whether that's deleterious materials, is to ensure that there's a very well experienced metallurgist who's consulted or part of the process throughout the whole to understand any application of any sort of regressions or recoverability assumptions that go into these models. All right, another challenge that we often see are in pegmatite dikes. These can be really challenging for selective mining. And whether this is open pit, as we see from the image below, or the challenges of trying to design underground operations and infrastructure to extract these very complex and sometimes discontinuous dike swarms. Because of the varying degree of thickness, continuity, so on and so forth, selectivity of mining, getting the iron and the host rock, country rock, out of the ore feed and trying to just take the lithium-bearing pegmatites in can be an absolute challenge. Obviously, for cost and for engineering purposes, we want to see larger equipment, higher volumes, but that may come at a cost of selectivity and the ability for the operators and the operations to remove these challenging rock types, right, in order to feed to the mill. So understanding the selective mining unit, what those considerations are across the whole deposit is absolutely key. Now, this relates right to what is our confidence in our drill spacing? What is our confidence in the multiple angled drill holes that we've gone? Has this whole deposit that we see on the screen here been evaluated using vertical drill holes? Well, you can easily imagine dropping vertical drill holes down a high wall in a case like this where you are all in pegmatite, you got nothing, a start at the top, and then it disappears, all nothing, all pegmatite. So, having multiple directions of angled holes coming from different azimuths, different dips, with detailed structure being collected on those drill holes is absolutely key to try to assess that 3D geometry, and thus the ability to mine and selectively mine these pegmatites is very important for successful operation. All right, so all of this goes into our classification, right? Or how do we assess risk from a mineral resource classification with these deposits? This can be absolutely challenging, especially in environments where we're a bit data poor, there's not enough drilling, or there's struggles and challenges associated with use of, say, RC drilling or historic work that's been done at a different scale. So the way that it is recommended when talking about classification or assessing risk associated with these projects is certainly a lot of transparency when it comes to the technical report on conveying and understanding the areas that are actual risk from the evaluation or the study stage, PEA, PFS, FS, into mining. And so it's always recommended that that qualified person not only be qualified and well experienced within these types of deposits, but then also has a good feeling of the impact of these different items as it relates to metallurgical recovery, to beneficiation, selectivity of mining, and ability to produce actual products in a positive economic manner. And so what we often see around the world with some of the large lithium pegmatite deposits is that they actually never have a measured resource. Now, I know for some QPs out there, they might be scratching their head saying, well, you drill it and you mine it, and what's the issue? But the ability to accurately predict at a measured level may never be able to be assessed with some of these deposits unless at a final ore control stage, right? At a level of, a few meters away from blast hole data, where you can accurately make that decision between potential ore above cutoff grade that's pegmatite and waste rock, internal dilution, barren rock, whatever it may be. And if that's the case, then QPs just need to be very transparent in how they assess and communicate that risk. And so just a bit of a word of caution to the QPs or the folks who are looking at assessing these is that it's not about drill spacing. Certainly, that is one of many, many aspects that goes into it. And oftentimes we don't know what the appropriate drill spacing should be until we're multiple benches deep, of course, right? But to really be realistic and transparent about considering all those different aspects of the geologic continuity, the understanding of structure, mineralogy, chemistry, so on and so forth, that goes into the assessment of classification. All right, so after all of that, what would you consider a good characterization? So if you've got a project, a lithium pegmatite project, and you're in the process of characterizing it, these are a few items that we see across the globe at various lithium pegmatite, either operations, projects, exploration, or whatever, that really do a good job of trying to assess this. One of the first ones is a detailed structural assessment of the property and of the entire district. Often working large scale into small scale is the way to go here. Lots of different ways to collect structural data depending on your deposit, whether it outcrops on surface, is undercover, is tropical, or barren of vegetation, whatever it may be. Geophysical techniques like magnetics can be very helpful, but then also just collecting as much structural data as possible from both surface and subsurface and drilling, and trying to create a good structural geologic model. Detailed mineralogy, absolutely key, of course, looking at characterization of both individual dikes, of dike swarms. What is lithium bearing? Is there barren dikes presence? What are the attitude characterization of those? And whether it's like a quartz bearing dike or late stage mafic dike. Understanding the geochemistry obviously is an important one. Using the right digestion, as we touched on. Trace chemistry, understanding the interaction between country rock and the pegmatites can be very important. Alteration associated with a halo around them can be important, especially if there's sulfides that are coming into the mix. And lots of diamond drilling. Obviously, budgets are always limited, but just understanding that diamond at multiple angles is the absolute key here. And being realistic about 3D modeling. We work the best we can when putting together 3D models. It's only as good as the data we put into it. So really focusing on using as much of that structural, mineralogical, chemical, diamond drilling, etc., to get into those 3D models to be realistic around continuity and extrapolation is absolutely important. So on the opposite side of that, common red flags that I've seen across doing due diligence on multiple properties is for obviously a lack of structural evaluation is going to be a major red flag. Not understanding being able to predict where these things are going, how folded are they, how continuous they are. Reliance on non-diamond drill core data is a bit risky, right? RC, we're missing a lot of information. And any other drilling techniques like percussion or just trenching. And again, for early days studies or exploration on a property, that's perfectly fine to start, but don't expect that data to translate well into a resource. Other red flags, just a lack of understanding of what those host minerals may be. Just testing everything on a lithium chemistry is okay, but you need to know what's hosting those chemistries, and can those minerals be recovered into a spodumene concentrate or whatever the final product may be. There are many properties around the world that have historically been mined for, say, tantalum, niobium, or tin. And then as the price of lithium's gone up, we've seen a sort of a pivot in focus. And so if there is a property like that is a historically mined, say, tin operation, just to understand the use of that historical data and was it correctly analyzed, tested, or is there impacts of using old chips from 10, 20, 50 plus years ago for reassay? So really working with the chemistry and the labs on that. Understanding of the emplacement of all these dikes, often these are very complex set of intrusives, is absolutely critical. Other red flags we see oversimplified 3D geologic models. In some cases, this is an absolute headbanger where you see a lot of good structural work, geochemical work, really detailed work on drilling, et cetera, and then it's thrown to an external resource geologist who puts it in the most basic, simplified, rudimentary 3D geologic model and loses the majority of that information. That doesn't help. So make sure there's good alignment between all of those groups. And then understanding the selectivity, whether open pit, whether underground, whatever it may be, and ability to remove those impurities from a geometallurgical perspective. Well, again, my name's Eric. I hope you enjoyed this video. Just sort of a brief high level of lithium pegmatites, the geologic characterization. If you got further questions, feel free to reach out to me anytime. My SRK email is right there. You can find me on LinkedIn as well. And a special thanks to a couple of my colleagues who reviewed this, gave me some good thoughts and some nice conversations. Martin Pittick, Matthew Hastings, and Scott Burkett. So thank you very much. Appreciate it, and have a great day.